Here's something most people assume about fine-tuning AI models. If you change what's happening inside the model, you change what it does. And if you change what it does, something must have changed inside. Internal change and output change, they go together. It's intuitive. It's also wrong. I'm Arshavir Blackwell, PhD, and this is Inside the Black Box. Today I'm going to walk you through a finding from our latest research, work I've been doing with John Holman, that has direct implications for anyone auditing, deploying, or regulating fine-tuned language models. The short version. What a model learns inside does not predict what it does outside. And at the scales where models are actually deployed, these two things can move in opposite directions. Let me show you what I mean. We ran 12 experiments. We took llama models at 3 scales, 3 billion, 8 billion, and 70 billion parameters, and fine-tuned each one on 4 very different text corpora using Lora adapters. Same configuration every time. Rank 16, attention only, 50 training steps. The only variable was the training data. The 4 corpora were chosen to be as different from each other as possible. Marcus Aurelius's Meditations, dense philosophical prose. Seneca's Letters, similar domain, different register, more epistolary. DTC ad copy, commercial product descriptions, the kind of language you see selling sneakers and skincare. And alpaca, Stanford's instruction-following dataset, which teaches the model to respond in a structured question-and-answer format. For each of the 12 resulting models, we measured 2 things completely independently. First, how much did the model's internal representations change? We used cross-coder feature analysis, sparse autoencoders trained on paired activations from the base and fine-tuned models, to decompose MLP layer changes into individual features. Second, how much did the model's outputs change? We measured KL divergence on next token predictions. Basically, how differently does the fine-tuned model predict the next word compared to the base model? Then we plotted one against the other. Internal change on the x-axis, output change on the y-axis. 12 points, 1 per experiment. If internal change predicted output change, you'd see a diagonal, points climbing from lower left to upper right. More change inside, more change outside. A clean, boring, expected correlation. That is not what we see. At 3B and 8B, everything clusters in the lower left. Modest changes on both axes, not much separation between the corpora. Nothing interesting yet. At 70B, the picture explodes. The 4 corpora scatter into 3 completely distinct regimes. And within just those 4 70B data points, the Spearman rank correlation between internal change and output change is negative 0.80. The corpus with the most internal change has the least output change, and vice versa. Let me walk through each one. DTC ad copy produces the most extreme internal change of any experiment, 340 times. That's the peak ratio of cross-reconstruction error to self-reconstruction error. The model is building massive new internal machinery for commercial language, entirely new representational geometry that didn't exist in the base model. But here's the thing. The outputs barely move. KL divergence of 0.478. Top token agreement with the base model is still 79%. If you ran a standard output evaluation, which is what most auditing frameworks do today, you would classify this model as essentially unchanged. An output-only audit misses the most internally transformed model in the entire study. That's the danger of latent divergence. The restructuring is real, it's massive, but it doesn't propagate to outputs in a way that surface-level testing can detect. Alpaca does the exact opposite. It has the lowest internal change at 7 dB, 39.8 times, modest by 7 dB standards. Yet it produces the highest output divergence of any experiment, KL of 1.41. Only 41% top token agreement with the base model. The outputs have fundamentally shifted. So what's happening? The adapter isn't building new features. A 70 billion parameter model already knows how to follow instructions. That capability is already encoded in the weights. What the adapter does is re-weight existing circuitry. It redirects features the model already has toward instruction-following formatting. It changes what the model does without changing what it knows. We confirmed this with CKA analysis, centered kernel alignment, a completely different measurement tool that doesn't use sparse autoencoders at all. CKA shows Alpaca has the highest late layer activation displacement, concentrated in the final 30% of layers. That's exactly the output generation zone. The adapter is reaching in at the end and steering existing representations toward a new behavioral target. An internal-only audit would classify Alpaca as the least modified model. The outputs tell a completely different story. Marcus and Seneca both land in the upper right. High internal change, high output change. But they get there differently. Marcus builds internal change steadily across scales. 12.5 times at 3B, 29.3 times at 8B, 77.1 times at 70B. Meanwhile, its outputs barely move through 3B and 8B. The model is quietly accumulating internal restructuring, building representational geometry for Stoic philosophy. And then, at 70B, the outputs finally catch up. KL jumps to 0.72. The internal change was there all along. The behavioral manifestation was delayed. Seneca couples earlier. By 8B, it's already showing substantial output divergence, KL of 0.49. At 70B, both metrics are high, 99.5 times internal change, KL 1.24 on outputs. These are adapters that genuinely construct new representational geometry, novel features, new internal circuitry, and that construction eventually shows up in what the model generates. The decorrelation isn't noise. It reflects two fundamentally different adaptation mechanisms. When a model encounters a domain it lacks the internal machinery for, the stylistic texture of Stoic philosophy, the register of commercial copywriting, the Lora adapter has to construct new features, novel representational geometry that didn't exist in the base model. This registers as high internal change. Whether it shows up in outputs depends on whether those new features get used in generation or remain latent internal structure. When a model already has the right machinery, and a 70 billion parameter model has encountered plenty of instruction-following data in pre-training, the adapter just re-weights existing circuitry. It doesn't need to build anything new. It redirects what's already there. This produces modest internal change, but can produce large output shifts. Construction versus reweighting. Two different mechanisms, and each one is invisible to the wrong measurement axis. We confirmed this causally, not just observationally. When we clamped the crosscoder identified features back toward base model values in Alpaca 70B, it partially reversed the output divergence. When we ran matched controls, random, same cardinality features, magnitude-matched Gaussian noise, nothing happened. The features the crosscoder identifies are carrying real behavioral load. Here's a prediction that sounds right, but is wrong. Models should build the most new features for text they find most surprising. High base model perplexity, bad token predictions, should mean the model needs more new machinery. At 70B, it's inverted. Marcus has the lowest base model perplexity, 4.4. The model predicts Stoic philosophy tokens quite well, yet triggers the highest novel feature surge. DTC has the highest perplexity, 14.5, but doesn't produce a proportionate surge. The correlation between perplexity and novel features is negative 0.80. This tells you something important. Perplexity measures whether the model can predict the next token. Feature analysis measures whether the model has the right internal structure to represent the domain. A model can be good at predicting tokens while still lacking the specialized representational geometry that fine-tuning carves. These are genuinely different questions. And I want to emphasize, this decorrelation only shows up at scale. At 3B and 8B, everything looks correlated. If you compute the Spearman correlation across all 12 experiments, you get positive 0.71, which looks like internal change and output change go together. But that's a scale confound. Larger models produce larger values on both axes simply because they have more capacity. Hold scale constant at 70B, and the correlation flips to negative 0.80. The regimes separate. The mechanisms diverge. This is not a smooth extrapolation from smaller models. It's a qualitative phase transition in how fine-tuning operates. Any auditing methodology validated only at small scale will miss it. The practical consequence is direct. Single-axis auditing fails. An output-only evaluation, which is standard practice today, correctly characterizes Alpaca and Seneca, but misclassifies DTC as unchanged. An internal-only evaluation correctly identifies DTC's massive restructuring, but misclassifies Alpaca as minimally modified. Neither axis alone captures the full picture. This matters for regulatory frameworks. The EU AI Act, Article 25, shifts governance obligations when a deployer substantially modifies a vendor model. What constitutes substantial modification? Our evidence says you can't answer that question with outputs alone, or with internals alone. A model that rewrites its internal feature geometry while maintaining stable outputs, that's substantial modification, invisible to output testing. A model that shifts behavior dramatically through minimal internal changes, that's also substantial modification, invisible to internal analysis. Our recommendation: auditing at deployment scale requires both measurements, internal feature analysis and output divergence evaluation, at a minimum of 2 network depths. The evidence package must include both axes. One more thing. We verified that the decorrelation isn't an artifact of the cross-coder methodology by running a completely independent measurement, linear CKA, centered kernel alignment, which compares activations without any sparse autoencoder involved. At mid-network layers, CKA agrees with the cross-coder metric. At late layers, they diverge, and the divergence is informative. CKA sees Alpaca as having the highest late layer displacement. The crosscoder sees it as having the lowest sparse feature change. Both are right. Alpaca moves activations globally without restructuring the sparse feature geometry. 2 different tools, same mechanistic story. So here's the takeaway. If you're auditing fine-tuned models, evaluating them for deployment, or building governance frameworks around them, the internal output decorrelation means you need to look at both dimensions. What a model learns inside does not predict what it does outside. The mechanism of adaptation varies by corpus, and each mechanism is invisible to the wrong measurement axis. Responsible deployment requires looking at both. This is Arshavir Blackwell, PhD, for Inside the Black Box. Thanks for listening.